The fifth generation of wireless technology, known as 5G, promises significantly faster speeds, lower latency, greater capacity, ultra fast downloads, and immersive experiences like augmented reality and virtual reality. But there's an important catch to consider. The fastest part of 5G relies on millimeter waves, which operate at very high frequencies. But these signals have a very limited range, typically only tens to a few hundred meters, and they are highly susceptible to obstacles like buildings and trees. So, what's really going on with mmWave technology, the key enabler for 5G's peak performance? Let's dive in and find out in detail. In this video, we'll thoroughly explore millimeter wave propagation characteristics, explain why mmWave is so crucial for achieving 5G's high-speed goals, and discuss the major challenges that engineers face in real-world deployment. By the end of this video, you'll have a clear understanding of why mmWave delivers such powerful performance potential, yet remains difficult to implement effectively across diverse environments. Millimeter waves, commonly abbreviated as mmWave, specifically refer to radio frequencies in the range of roughly 24 GHz to 100 GHz, with wavelengths measuring just 1 to 10 millimeters. These mmWave frequencies are dramatically higher than the traditional cellular bands operating below 6 GHz, which have much longer wavelengths and different propagation behaviors. Because the wavelength at mmWave is extremely small, in the millimeter range, it enables us to pack an enormous amount of data into the signal, supporting massive throughput. The primary advantage of mmWave and 5G networks is the availability of massive contiguous bandwidth in largely unused spectrum, which allows for extremely high data rates essential for bandwidth-intensive applications. Under ideal line-of-sight conditions, these data rates can reach up to an impressive 10 to 20 gigabits per second, thousands of times more than lower-frequency signals. Despite these compelling benefits, mmWave technology encounters significant propagation challenges stemming directly from its high-frequency physical characteristics, such as severe attenuation. One key limitation is that mmWave signals have a very restricted range, typically only spanning tens to a few hundred meters, far shorter than the several kilometers possible with sub-6 GHz signals. These signals are easily absorbed, scattered, or blocked by common physical objects including buildings, trees, walls, foliage, and even human bodies, leading to high path loss. Unlike lower frequency signals that can diffract and bend around obstacles, mmWave requires a clear line of sight path, and weather like rain can cause additional severe attenuation of 5 to 10 decibels or more. A helpful and intuitive analogy for understanding mmWave propagation is to compare it to a laser pointer versus a traditional flashlight in terms of beam characteristics. The laser pointer represents mmWave, precise, focused, and capable of high intensity over short distances, but completely blocked by even small obstacles, while the flashlight mimics sub-6 GHz, spreading light widely, traveling farther, and bending around objects. To effectively overcome these propagation limitations, advanced technologies such as precise beam forming and massive MIMO antenna systems are widely employed in mmWave deployments. Beamforming works by electronically steering and focusing the signal beam directly towards the intended user device, thereby optimizing signal strength, extending effective range, and minimizing interference from other directions. Massive MIMO leverages a large number of antennas, often 64 or even hundreds at the base station, to transmit and receive multiple data streams simultaneously to various users, boosting capacity and spectral efficiency. Given the inherently short range of mmWave signals, deploying a dense network of small cells, low-power nodes spaced closely together, is essential for achieving reliable widespread coverage, particularly in urban settings. Modern 5G networks adopt a smart hybrid approach, strategically combining high-capacity mmWave with the broader coverage and penetration of sub-6 GHz frequencies for optimal performance. This hybrid strategy ensures seamless continuous connectivity as users move, while fully leveraging the unique strengths of both frequency bands in their most suitable scenarios. Looking ahead to the next evolution in 6G, it builds directly on mmWave foundations by incorporating even higher terahertz frequencies above 100 GHz for unprecedented capabilities. While promising dramatically greater speeds, potentially up to terabits per second, these terahertz frequencies in 6G will introduce even more extreme propagation challenges, including even shorter ranges and higher sensitivity to blockages. Emerging solutions for 6G include AI optimized dynamic beam tracking for mobility and reconfigurable intelligent surfaces, known as RIS, to enhance signal paths. RIS consists of programmable metasurfaces installed on structures like building facades, capable of intelligently reflecting, refracting, or manipulating mmWave or terahertz signals to bypass obstacles and reach receivers efficiently. mmWave technology proves particularly impactful in high-density environments where user numbers are large and demand for ultra-high-speed data is intense, such as busy urban centers. Ideal applications include city hotspots, crowded stadiums like those with NFL games where Verizon has deployed mmWave, and airports, supporting massive bandwidth needs for 4K streaming, social media, and AR/VR experiences. In these scenarios, mmWave effectively complements low and mid-band frequencies by delivering ultra-fast internet precisely where and when it's needed most in specific high-demand zones. Overall, millimeter wave technology remains fundamental to unlocking the full high-speed and high-capacity potential of 5G networks, with its core principles becoming even more critical for the ambitious goals of 6G. Although significant challenges persist, innovative engineering solutions like beamforming, massive MIMO, dense small cell networks, hybrid spectrum strategies, and emerging RIS technologies are being actively developed and refined. These ongoing advancements collectively pave the way for a transformative future of ultra-fast, highly reliable, and deeply immersive wireless connectivity. Don't forget to like and subscribe for more in-depth tech insights.